everyone. Free organic lab lunch. Okay. I'm Matt Petrovich, and I'm aware I've talked to some Orgo sections before about this, but to just try and make sure I can get everybody to hear about it. This will be the last time you hear my recruitment speech about this, so I'm here to talk to you about Relay for Life, which is a cancer charity we like to hold every year here at Hope College. And we actually like to make it sort of a competition who can raise the most money, and we divide it into teams. I'm here to talk to you about the Hope Science Team, Team Hope Natural Science. I'm team captain for that, as well as Richard Edwards. And so the team, we like to get together and hold just several fun fundraising events. You may have witnessed these last year or not. But we like to do Pie Professor, where we invite several organic professors and President Knapp himself to take a pie for charity. It's a lot of fun. Not just organic professors, but everybody loves it.
You need to encourage all your professors to participate.
It's also after organic exam too. But another event we like to hold is the pancake dinner. So that's right smack dab in the middle of midterms. We have pancakes and bacon, and we'll be selling them for charity. It'll be fun. Right after a midterm, go eat bacon, get recharged for more study, more midterms. And then we like to hold a euchre tournament right at Relay for Life, which is November 13th. You can enter a chance to win prizes, and it'll be a lot of fun. So if you're interested in going to any of these events or helping set them up, you can go ahead and contact me at matthew.petrovich@hope.edu or Richard at richard.edwards@hope.edu. Thanks for taking time to hear from me, and let's do organic chemistry.
Yeah.
And are you having a meeting before that or no?
We will
Just contact you?
Yeah, just contact us.
Show us the tab.
How does that help charity?
Just advertising.
Okay, you guys, I'm feverishly getting everything up here. The boards weren't left very tidy, so I'm clean them first.
No, I had an Orgo lab. Next week is my latest week of the entire.
All right. Okay, so let's talk about all the announcements on the board first. This week we're going to finish experiment 3, so we're going to do part 2 of experiment 3 this week in lab. We'll also be talking about your conclusions for experiment 3, because in a little bit here you'll find out that your report is due soon for experiment 3. Quiz number 4, make sure, as always every week, bring your calculators for the quiz and other calculations in lab. Your report for experiment 1 is due this week, so you will be leaving us your notebooks when you go to leave lab this week with your report completed and inside of there, okay? So don't forget to give us your notebooks and have those ready to go when you come to lab this week. Next week, we've got fall break already upon us, next Monday and Tuesday. So there's no formal organic lab because we don't have a Tuesday lab. We don't have a Tuesday in the week. We're not gonna have a Thursday lab, okay? So there's no pre-lab lecture next Wednesday when it's actually Monday schedule, which is extremely confusing. But no pre-lab lecture next week. Go to workshop instead. So if you have workshop at 4 o'clock on Wednesday, go to your 4 o'clock workshop next Wednesday. What we will have next week is we'll have open lab. So Wednesday and Friday next week, regular hours 9:30 a.m. to 3:30 p.m. On Thursday, because you'll be back from break, but we're not going to have a formal lab, that labs will be open from 9 a.m. to 4 p.m. on Thursday, October 8th, okay? And so you may want to take advantage of some of this. We'll talk about here in a little bit. We're going to need you guys to collect some masses and melting points. So this would probably be a good time to do that. Then in 2 weeks, so the next time that we all see you again after this week, we will be doing experiments 5 and 6 that week. The actual doing of the experiment is experiment 6. And so that's what you're going to prepare your pre-lab for, is experiment 6. Experiment 5 is going to talk about the technique of IR spectroscopy. So you'll learn about that as well. Also in 2 weeks, so the reason we're going to talk about your experiment 3 conclusion is in 2 weeks, your experiment 3 report is due. Okay, so the week you get back from fall break and have lab, your experiment 3 report is due. So October 13th and October 15th. October 13th for the Tuesday labs, October 15th for the Thursday labs. Your experiment 3 report is due. So I want to make sure everyone, I got kind of at the end of the board, so I want to make sure everybody hears that. So you've got that written down, all right? Okay, we're going to talk about the second part of experiment 3 today, but I want to make sure everybody understands what they need to do with the trimeristin that they collected last week, okay? So with that trimeristin, hopefully it is now dry after you let it sit in your drawer over the week. You need to weigh what you've got, okay? And see how much trimeristin you have. You need 1 gram for the part 2 hydrolysis reaction. Okay? So if you're less than 1 gram, you need to talk to your instructor right away. But you need 1 gram for the part 2 hydrolysis reaction. You also need to set aside 0.05 to 0.1 grams for melting points. Okay? We think we have isolated the trimeristin, but we need to verify what it is, and so we're going to use its melting point to verify that it is trimeristin. Okay? So we're not going to collect the melting point before you go on with the hydrolysis reaction. You need to just set that aside. So going into the hydrolysis reaction, you need to know how much you are using. It's being used for the hydrolysis reaction. So make sure you've weighed it, you've set aside your little bit, and then you know exactly how much you're using for the hydrolysis reaction, for the part 2 reaction. Okay? Now, if you have more than 1 gram, after you've set aside your little bit, then you have your amount ready to go for your hydrolysis reaction. If you still have more than 1 gram, we'll take donations from you for the other people in your class that may not have a full gram, okay? So if you ended up getting more than 1 gram dry out of the nutmeg from last week, we will take donations from you. But what you do need to know is how much dry trimeristin you were able to extract, because you need to calculate that extraction yield, okay? So do know what that weight is of the dry trimeristin, all right? So you get that data point calculated. Then you can make sure you have the gram, make sure you set it aside. If you can donate to other people, that would be great, or the people that don't have enough will, of course, accept donations, all right? And then just make sure we don't lose this little bit that you're setting aside for melting point. So put it somewhere safe so that you can go back to it once you are done with the hydrolysis reaction. Okay? And so part 2's reaction, we're going to take our trimeristin and convert it to myristic acid. And this is known as a hydrolysis or a saponification. So we're going to make soap in this reaction, right? And so this is the process that you go through to make a soap. Soaps are made from basic hydrolysis, which is what we are going to do this week, basic hydrolysis, meaning we're using a base, not that it's easy. So if you were to make soap at home, you would hydrolyze with base naturally occurring fats to form this, to form your soap. And so what you are making is the sodium salt of the fatty acid, okay? Okay, and so like our fatty acid that we have in the end, we've got the CH3 group, then this 12-member CH2s in the middle here, and then in the end, here we've got the sodium salt, okay? And so if you look at this in general, you got this charged part, and then just kind of this very organic-y part that's the long tail to it, all right? And so you've got something that's very hydrophobic, and then something that really, really likes the water on the other end. And so what happens is the way the soaps work is they form what's called a micelle, and so they stick their, the part that doesn't like water in the inside, and they stick the part that does like the water on the outside. So say we've got a piece of dirt here. A soap would work by putting its long tail on the inside around the dirt, and then it puts its water-loving head on the outside, and that's how you help carry dirt away, is from this micelle, okay? And so you'll learn, I mean, if you take biochem, you'll learn much more about micelles and lipids and so forth. But that's how it works. It's called as by this micelle. And so what happens is the soap solubilizes something that is not soluble in water alone, like dirt. Or an oil. And so we're going to do the same thing with our trimeristin. Now we're not then going to use it to actually have it act as a soap, but what you will see are soap-like properties as you're going through the process of hydrolyzing your trimeristin, okay? And so, for our hydrolysis reaction, one thing that is really important is stoichiometry. So you got to keep track of your stoichiometry. So we didn't leave that in Gen Chem. We need to keep track of it this week, all right? So kind of star that, and I'll show you all the ways that it is very important. We're starting with our trimeristin, okay? So remember, it's the triester, okay? So we haven't broken it apart yet. And remember, everything is linked at our terminal methylines off of our ester. Okay, so here's our trimeristin. what we are going to do is we're going to react this with sodium hydroxide, so that's our base for our hydrolysis, and we're going to use ethanol as the solvent, all right? Okay, we've got three, it's a triester, right? So in order to get this reaction to work, we don't need just one sodium hydroxide, we need three of them. So this is right from the get-go where the stoichiometry comes into play. So every one trimeriston, we're going to need 3 sodium hydroxides, all right? And we're going to, like I said, we're going to have sodium hydroxides in water. Then we've got ethanol as our solvent. And we're going to use a new term as far as technique. We're going to use what is called reflux, okay? And so in a little bit here, I'll show you that apparatus and show you what's involved with the reflux. But we're going to be heating this solution, and you want to watch what happens during the process, okay? Because you're changing this trimeristin from something that is not super water soluble into something that hopefully is very water soluble. So you should see changes between when you start the reflux and when you get to the end of the reflux, all right? So you're going to cut off this piece. We're going to cut off our glycerol, and then we're going to have individual sodium salts of our fatty acids, okay? So we've got our glycerol piece. All right. And then we're going to have our sodium myristate, which is the sodium salt. But remember, we've got one glycerol, but we're going to have, because we had 3 of these, we're going to have 3 sodium myristates, okay? This is water soluble. This is not water soluble. Or not really easily water soluble. All right. So you should see the difference in between the two. Okay. Now, what we don't want the sodium salt in the end. We want something that is actually a solid in the end. So we have to do something to the sodium myristate to then make it a solid so we can work with it and filter it and get its melting point. So now we're going to take our sodium myristate and we need to add HCl to it, all right? So we have 3 sodium myristates, so we'll need 3 equivalents of HCl, and then we will get to our myristic acid, okay? And when we get to our myristic acid, it's not going to be very soluble in water. So then we'll be able to filter it, okay? And once we isolate our myristic acid, we're going to also clean it up. We'll recrystallize it to purify our myristic acid, all right? And so for general mechanism, you guys, I know, haven't really gotten to mechanisms so much in lecture, but in your textbook is the general mechanism for the basic hydrolysis of an ester, okay? So on In the 6th edition of Murray, page 792, or the 7th edition, page 810, has this figure, okay? And so what is happening, here we've got our ester, so that would be our triester there. We have the OH attacking the carbon of our carbonyl, and then we then have the carbonyl reform, and we give off our OR minus group, and we form our carboxylic acid, okay? Then we need to go, because that then will deprotonate here, we need to add acid to finish off this reaction and protonate everything and end up with our alcohol that came off, so that's our glycerol, and our carboxylic acid, which is our myristic acid, okay? So in second semester, you will get into more detail of this mechanism, but this is in your textbook in case you want to look over that, okay? So a couple things we want to consider with this in this whole process. Oops, we got even more math. We're going to learn extra bonus things in organic lecture today. So this reaction we're going to be doing at reflux. So let's talk about reflux first. What that means, okay? Reflux is a way to keep a reaction at a constant temperature. So that's what you use it for, is heating a reaction at a constant temperature. And that constant temperature is the boiling point of the solvent. So in our case, it's the boiling point of the sodium hydroxide ethanol mixture. That is what temperature we're going to heat this reaction at, okay? And so when you have a solvent boiling, can you get any hotter than that solvent as long as the solvent's present? No, okay? And so the reaction will stay at that constant temperature as long as you're condensing the solvent and the solvent isn't going away, okay? So that's the key to this, is we can't lose our solvent. So we can't just heat the reaction mixture and let everything disappear. We have to condense our solvent and get it back into the reaction mixture again. So it's the boiling and condensing of the solvent to keep things at a constant temperature, keep your reaction at a constant temperature, that's involved with reflux, all right? And so that setup that you're going to use for reflux is a new setup that you have not used before, all right? And so this is what the setup will look like. You can either set it up this way with just the heating mantle and a ring clamp underneath it, or you can set it up so that you've got your heating mantle on your stir hot plate, and then just make sure you have a stir bar in your reaction flask, okay? So if you have it on your stir hot plate, then you're going to put your heating mantle right on top of there. Don't put the ring clamp in there, okay? Clamp your reaction flask really well, and this is where your trimyristin and your sodium hydroxide and your ethanol is all going to go for the reaction, all right? Then you're going to use your condenser and make sure it is nice and vertical on top. So we don't want any leaning condensers. We want nice and vertical for a reflux apparatus. I tend to, because you get more water pull through it, I always use the larger condenser for a reflux as well as a distillation when possible. So I would use the Liebig condenser for your condenser for this apparatus. And you're going to have a second clamp on that condenser, but you don't want it tight. You want it there just to support it. And what you want to be able to do is take this whole apparatus when you're done with the reflux and be able to pull it out of the heat. So if you unclamp things here so that you can raise it up, keep your reaction flask clamp, but loosen it from the ring stand. If this clamp is loose, you'll be able to raise the whole apparatus up and be able to pull it out of the heat really easily, okay? So this clamp is tight on the reaction flask. This clamp is loose on the condenser, so you can move the condenser up and down, all right? The other thing that's really important is we're fighting water, or fighting gravity with our water, so water in on the bottom, water out on top, and we don't put a stopper on the top, because if we heated it with a stopper on the top, we would have something that would be kind of bomb-like explosive, because you'd be heating a closed system, okay? So we don't want to heat a closed system, so nothing on top of your reflux apparatus, all right? When you get this all set up, before you start heating, we'll come around in lab this week and check your setup and make sure the setup is okay, all right? Okay, so that is the reflux setup. So that is what you're going to be using for this reaction here, all right? Then, after the reaction, the rest of what you will be doing should be shown in your flow diagram for part 2, okay? So here is our reaction mixture now, okay? We've got our glycerol, our sodium myristate, any organic impurities we have, ethanol, water, and sodium hydroxide, okay? So our flow diagram starts at that reaction mixture at the end of the reaction, all right? The first thing that you are going to do is then use the HCl to make a solid, okay? And a couple notes with that HCl. First of all, our reflux is going to last for 45 minutes, okay? And the 45 minutes is when it starts boiling and condensing, not when you turn on the heat, okay? Another thing I forgot to mention about the reflux is you're going to use your ohmite, which is the variable voltage controller on the side of your hood. Don't plug the heating mantle directly into the wall socket, the regular outlet. Plug it into the ohmite. You turn the switch on with the ohmite and control the voltage for heating, okay? So make sure you're plugging into the ohmite, not into the wall socket. If you plug it in the wall socket, your heating mantle is going to get really hot really fast, hotter than you want it to be, okay? And then, like I said, this starts when the boiling and condensing starts, okay? That's when your time starts. And you want to keep an eye on it as well, because sometimes your reflux will start kind of vigorously, so you turn down the heat a little bit. Make sure you keep it boiling and don't let it die out, or you'll have to start that reflux time, add on to that reflux time, okay? So keep an eye on it when it's refluxing. With the HCl, make sure you want your pH to be below 4, okay, when you are adding the HCl. So make sure that you do use the amount of HCl it tells you, but also make sure, stir and check the pH for when you are adding the HCl to your mixture, so you get all of your myristic acid to crash out, okay? The other thing is you're going to be using ice cubes in the beaker with this whole mixture in it. You're going to vacuum filter when the ice cubes are melted, okay? So don't try and filter it with ice cubes still in the mixture, okay? Everything needs to be melted, and then you will filter it, all right? So that is this portion. That's this portion here, okay? So we filter, and we'll get our myristic acid and other organic impurities and water, because we're filtering out of an aqueous solution. The ethanol, the glycerol, the water, other water, sodium chloride, and HCl should go into the filtering, all right? So then the last part is the recrystallization of the myristic acid. And that you also need to be really careful with, okay? Make sure you follow the directions really carefully, okay? As always, you should follow directions in the lab manual, but make sure you really follow directions in the lab manual, okay? So, we are using methanol as our recrystallization solvent, all right? But our solids melt at a lower temperature than methanol boils, okay? So trimyristin melts around 56 or so. Myristic acid melts around 54 degrees, okay, which is lower than the boiling point of methanol. So we are heating to about 50 degrees. So that means you're going to have to put your thermometer in your methanol when you're heating it on your hot plate and heat it only to 50 degrees. You don't want it hotter than 50 degrees. What will happen is if it's hotter, when you go to put the solid into the methanol or the methanol into the solid, you're going to get that solid to melt instead of dissolve, and so you'll get oil droplets forming instead of making a solution of the methanol and the myristic acid that you're trying to recrystallize, okay? So be really careful about this temperature. This temperature is really important, and use your thermometer to check it, all right? It also mentions using a hot filtration. Check with your lab prof before you do that, okay? It is really easy to make this crash out with a hot filtration, and so you want to make sure that you're doing a hot filtration only because you need to do it, okay? Don't do the hot filtration in a case that you don't need to actually do it. So ideally, in this 50-degree methanol, you get all of that solid dissolved, all right? If you really can't get all of the solid dissolved in the methanol, then you are going to have to use that hot filtration. Be careful with that. So be careful with the heating, be careful with this, all right? Now, we need to characterize our solids that we have acquired for this experiment, okay? So first of all, we're going to need what mass, what weight we got for the trimyristin. And from that, we will calculate our extraction yield. Then we need to characterize the trimyristin by melting point. So you need to collect the melting point range of the trimyristin. Now the myristic acid, the trimyristin, they melt, low 50s. So you don't need to get a fast melting point and a slow melting point to figure out what range they should be melting in. You know what range they should melt in, so you should be able to just collect a slow melting point range for the trimyristin, okay? And if you don't have time to collect the melting point range in lab this week, then you'll need to do it in open lab either this week or the times that it's open next week. Because remember, your lab report's going to be due the next time you are in lab again, okay? For the myristic acid, we'll need a mass, okay? And with that, we need to calculate a percent yield. So make sure you understand from the pre-lab, that calculation is all given in the pre-lab that was in your lab manual. make sure you understand that calculation. You need to recalculate it based on the amount of trimeristin you actually use for the hydrolysis reaction. So that's why it's really key to know the weight going into the reaction so that you can calculate this percent yield, all right? Okay, you're also going to need the melting point for the myristic acid. Now, these are very close. They differ by 2 degrees literature-wise, okay? So you want to make sure you gather the melting points individually, but you also need to verify that the myristic acid that you've collected is not just trimeristin that never got hydrolyzed, okay? So with these melting points, how would you verify that they are different from each other and not the same? Mixed melting point of, you don't have any standards either. There's no trimeristin standards or myristic acid standards.
Mix the two of them.
Right. The two of them together should, what should that mixed melting point do?
Drop lower,
It should,
broader.
it should be lower and broader, right? So you want to use a mixed melting point in the opposite way of what you used it for experiment 1, right? Okay? So make sure that you prove the solids are different, okay? Now, in writing your report and your conclusion, you can also use your observations that you have for the hydrolysis reaction, because you should see changes occur in that hydrolysis reaction. So make sure that you are recording observations as that reaction is occurring, because that's also support to something happened, something changed over the process of that reaction, all right? Okay, and then just remember, that lab report is due in 2 weeks. So these melting points, we gave you time for experiment 1 to collect melting points to make sure you were good using the instruments and everything was good with collecting your melting points. Now we're going to have you either be collected at the end of the lab period this week. You could probably get your trimeristin, but your myristic acid will still be wet, so you'll need to come into open lab to be able to collect those melting points, all right? So make sure that you get those melting points collected so you're, keyword here, due in 2 weeks. So you have all the data that you need. The other thing I was going to announce is make sure that you hang on to, so for experiment 1, hang on to your carboxylic acid and your neutral compound until you get your notebook back, in case there is any question about identity or melting point ranges or anything like that that your lab prof wants to look at with those solids, okay? Same with experiment 3. Hang on to the trimeristin, hang on to the myristic acid, even once you've collected the melting points, you have the masses, you have all the data you need, hang on to them until you get your notebook, your report graded and handed back to you, in case there's any question about what data you collected, okay? So as a safeguard, make sure you always hang on to those solids, and then once you've got your report back, then you can go ahead and dispose of those, all right? Questions you guys have? Good? Okay, so I won't see you next week. I'll see you in 2 weeks for lab lecture.